Hi, I'm Jimmy, aka Perceptes. In this video, we'll be diving deep into Warp 1, a waveshaper Eurorack module from Joranalogue Audio Design. Warp 1 offers many possible applications in processing both audio and control signals, as well as some handy utilities not usually found in a waveshaper. We'll start with some clips of the patches we'll be exploring. If you like what you hear, stick around for the details. In this video, we're going to go through all of the patches that are suggested by Joranalogue in the user manual for Warp 1, as well as a few additional ones. But before we do that, let's do an overview of the module to explain its feature set and the user interface. Warp 1 is a waveshaper, which is a processor that takes an input signal and modifies the input wave to create a different shape. It can do this by skewing, scaling, bending, and moving the waveform in different ways. In particular, Warp 1 is using analog circuitry to perform a mathematical function, which I'll display here on the screen. Now, I don't have a strong background in mathematics, so I probably won't be able to give you a lot of detail about sort of the mathematical and theoretical aspects of Warp 1, but I don't think it's super important to understand the mathematical details in order to understand how to use Warp 1 and how to get interesting results from it. But this is the formula that's being computed by Warp 1 on its input signal, where x is the value that's coming in on the input. Each control on the module affects a different component of this function, and that allows you full control over how the function processes the input to create different outputs. I've got a triangle wave coming out of plates going into the input of Warp 1, and then the output going out through data and into the quad VCA, which I'm just going to use as a simple level control. The green trace on data is the raw triangle waveform coming out of plates, and the blue trace is the output of that waveform as processed by Warp 1. The main component of Warp 1 is the exponent control, this potentiometer at the top. It's set to 1 in terms of the mathematical representation when the knob is at noon. As you turn counterclockwise, you get what Joranalogue calls concave curves. You can see that the wave is starting to bend and flattening out, and then in an extreme, the mathematical setting is 10, which gives us a completely flat, silent wave. As we turn clockwise from noon, we get a soft clipping curve that creates what Joranalogue calls convex curves. And the farther we turn, we get down to an exponent of 0.1, and we get something that's very close to a square wave. You can use the CV input for the exponent, and this allows you to go past 0.1 on the clockwise end. The second knob is the symmetry control, and all this does is it applies a DC offset to the input signal. So if you watch that blue line as I turn to the left, we're giving a negative voltage and offsetting that direction. Turning to the right will give you a positive voltage that'll offset in that direction. And in the center, there's no offset at all. There isn't a direct CV input for symmetry, but there is a second input, and these two inputs are actually identical. So you can use them to mix two completely different waveforms, or you can use it to mix one waveform and a CV signal. If you use a DC voltage into the second input, then you're effectively controlling the symmetry because all it's doing is essentially normaling a 5-volt signal to that input jack with an attenuverter. Scale is the third and final parameter exposed by Warp 1 to control its mathematical function. It's sort of like a VCA or an attenuator in that it affects the amplitude of the wave, but it also affects the shape of the wave as controlled by the exponent. If we turn it from center while the exponent is in the center position, then you don't see much of an effect. But if we turn the scale knob and the exponent knob in the same direction from Noom, then it will accentuate the effect of the exponent. So if I turn left on the exponent, as you can see, that blue line is pretty close to flat, and it's really hard to see exactly what it's doing. But if we turn scale to the left, then it really accentuates the peaks there. And so we can get a much stronger signal. You can see it starts to clip as the top edges hit positive and negative 10 volts. So scale will sort of change the shape and the position of the waveform. And then similarly, if we turn exponent clockwise into that soft clipping curve and then start turning the scale to the right, it'll behave more like a traditional gain control where the amplitude of the wave gets greater. But it also changes the shape a little bit, which you can sort of see there. Let's actually turn on the sound here so you can listen to the sound of this triangle wave being affected by warp 1. So here's our normal triangle sound. And if I turn exponent to the left and then scale to the left, you can hear those extra harmonics being added by the function. And then similarly to the right, you just get that extra saturation from the soft clipping curve. The scale control also has a dedicated CV input, so you can control that with an external modulation signal. Although when controlling with the scale input, you're restricted to values of 1 volt or greater only. There's a couple of other ways that you can fundamentally change the wave with warp 1. One is by switching the direct and hyper toggle in the top left corner. What this will do is it'll change the sign of the exponent. By default, the exponent is positive when you're in direct mode, but when you flip to hyper, the exponent becomes negative, and the exponent control now gives you a completely new set of shapes as you blend from counterclockwise to clockwise. You can see that the signal is much louder, and the shapes created are very different than they are in the direct mode. What's happening here is that the volume becomes much louder when the input signal is closer to 0 volts. So you get these extreme fluctuations in amplitude. Let's listen to the sound here. You also have a DH input, which can be used to send a gate to toggle the position of the switch. So regardless of which position the switch is in, a high gate into that input will switch it to the other mode, and then when the gate goes low, it'll switch back into the position that matches the switch. The second way that we can fundamentally change the output of the function is by turning on the absolute value switch. This is a full wave rectifier, and what that means is it'll take the part of the signal that's negative below the 0 volt point and invert the polarity of it so that those signals are the same values but positive above 0 volts. And you can see as I switch it on and off, we're essentially doubling the rate of that triangle wave because the points below 0 volts become positive. So you can use this with an audio signal to double the frequency, essentially moving the pitch up an octave. Or you can use it to remove the negative portion of a control voltage, which is commonly used to create a unipolar LFO from a bipolar one. The last two potentiometers on warp 1 are negative and positive clipping circuits. This is really interesting because it allows you to control the cutoff point of the negative portion of the signal and the positive portion separately for a great range of wave shapes on top of what the function produces. Clipping will, when brought up on the negative side, flatten out the bottom edge of the curve and just cut it off at the point that you specify, going all the way up to 0 volts. So similarly to the absolute value switch, you can use the negative clipping to get half rectification, where we cut away the negative parts of the signal, but rather than flipping them positive, we just ignore them. So we're not doubling the frequency, we're just ignoring the negative part of the signal. But this will also allow you to go anywhere in between. And let's listen to the sound of that. So this will introduce new harmonics, and it will also reduce the amplitude. The positive clipper does exactly the same thing, but in the other direction. So it'll start to clip above 0 volts, all the way down to 0 volts. So if you turn the positive clipping all the way down and the negative clipping all the way up, you're essentially silencing the output. Both the negative clipper and the positive clipper have CV inputs, so you can control these with external modulation. There's also an LED that gives you a visual indication of what type of clipping is happening. Blue means that the negative clipper is in effect. Red means that the positive clipper is in effect, and they can both be on at the same time. And if you're not clipping at all, then the LED will be white. So those are the basic controls of Warp 1, but it's got a couple of extra tricks up its sleeve. So far we've been using this output here, but there's also an inverted output. So if we take that out of the module, this will invert the polarity of the output wave, giving you a different version that you can use for any other purpose. This works exactly the same way, but just the positive and negative portions of the signal are reversed. And these can be used simultaneously because they're two separate outputs. Although keep in mind that combining them together, they'll cancel each other out. The other handy utility that Warp 1 provides that brings it beyond the normal function of a waveshaper is this polarity output. This is actually a comparator circuit that's built into Warp 1. If we take that output instead of the regular output, you'll see a square wave. And what this is doing is it's comparing the input signal to a fixed threshold at 0 volts. So anytime the input signal is above 0 volts, the polarity signal will be positive, and anytime it's 0 volts or below, the polarity signal will be at 0 volts. And the result is that you get a square wave from any of the input. You can use a DC offset or the symmetry control to change the position at which the input signal crosses 0 volts, and the result is that you change the width of the pulses in the square. So if we listen to this, what we're getting is pulse wave modulation on a square wave. And because this is a separate input, it can be used alongside the regular output and the inverted signal. You can use this for logic functions or just as an additional oscillator. Because Warp 1 is DC coupled, it can process both audio and control signals. In the manual, Joranalogue suggests this as the first example patch, processing an envelope to create new shapes. We're taking a simple attack decay envelope out of Quadrax, which is represented by this green trace at the top of data, and we're sending that into the input of Warp 1, and the output blip back into that blue trace, which we're then sending off to be used elsewhere in our patch. The green signal is going to be used for the amplitude CV for the VCA, and the blue one we'll use for a filter. You want to set the scale parameter so that it matches the peak amplitude of your envelope. In this case, that's 10 volts, so I've turned the scale all the way up. And then if we start turning the exponent knob to the left, we'll see that the curve of the decay changes so that we get an exponential envelope based on the linear one, but it doesn't change the timing of the attacks or the amount of time it takes to reach the 0 voltage level. If we turn to the right of center on the exponent knob, then we get logarithmic curves on the decay. So you can use this to create completely different shapes based on a linear input signal. Now in this case, I'm using an envelope generator that does have control over the type of curve, but in case you just have a simple envelope that only controls the time of the rise and fall, then this allows you to get those types of curves from that signal. Alternatively, and as we've done here, we can use the original signal and the modified signal for two separate purposes. So if I bring in the CV amount, then we're applying that green envelope to the VCA, increasing and decreasing the volume of this sequence from plates. If I then take this second output that's been processed by Warp 1 and set into a filter that I have off screen, let's bring the low pass all the way down and then increase the modulation amount. So now we have the original envelope, the green trace, affecting the volume, and the processed signal, the blue trace, affecting the filter cutoff. And as we change the exponent, we can now differ the two envelopes to control the filter cutoff and the amplitude with similar timings, but different curves, affecting the sound in more interesting ways. Another patch suggested by Joranalogue in the user manual is one that we kind of already talked about in the module overview, and that's using the comparator circuit applied to a triangle wave or some other input to create a square wave that allows you to modulate the pulse width. We've got a sequence playing on plates, and that's just a triangle wave coming into data on this green cable and going into the input of Warp 1. We're then taking the polarity output into the blue trace and off into our mixer. So that's a square wave being created from a triangle wave by comparing the voltage of that triangle wave and seeing if it's below or above 0. When it's above, we get a high gate. When it's below, we get a low gate. But then, if we take a DC offset into that second input, or modify the symmetry control manually, we'll change the points at which the voltage is above and below on the input signal, creating different widths of pulse on the blue trace. So let's just try it manually. And that gives you timbral changes in your square wave. But of course, sending a control signal allows you to automate this so you don't have to touch the knob with your hand. So I've got an LFO coming from off screen, going into the second channel of the quad VCA for attenuation, and then going into our second input. If I then bring in some of that signal, then you'll see the pulse waves start to animate to give some motion to our sequence. You can go pretty far with this and actually get to the point where you reach silence because the pulse has become either 100% or 0% of its full cycle. But it's up to you how much of this you want for the sound you want to create. The last patch suggested in the Warp 1 manual is to do half and full wave rectifying using the techniques that we covered in the overview. So here's a musical example of that. I've got some chords playing in the chord mode on plates. That's going through a VCA, adding a little bit of reverb. And then I've got a sine wave LFO synced to the tempo that's coming out of channel 1 of Quadrax. That's going in to our first channel of data, that's the green trace. And then we're sending that into the input of Warp 1 and the output of Warp 1 back into the blue trace on data, and then into the depth control on our VCA. I've added a horizontal line across the 0 volt position on the blue wave just so it's really clear which part of the wave is positive and which part of the wave is negative. So in this case, we're starting with a bipolar LFO, going above and below 0 volts. So if I take away the reverb, then you can hear that when the LFO is in its negative position, the sound of the chord goes away completely. I've set the offset on the VCA to noon, so essentially the default value of the audio should be about 50% of its volume. And then when the light goes green during the positive part of the LFO, we get an increase in volume from that position. And when it goes red during the negative portion of the LFO, we go counterclockwise essentially from that offset position and bring the volume all the way down to 0. So what if I didn't want the effect to be so strong? I didn't want the volume of the chord to duck away entirely. Well, I could just use the attenuator on the CV input. But the problem with that is that it affects the entire strength of the signal, both positive and negative. So maybe I want it to continue to get as loud as it was before, but just not get so quiet during the negative portions. We can use half-wave rectifying to do that. If I start to bring up the negative clipping on warp 1, we'll start to see that the bottom edge of that blue waveform is truncated. So there's about halfway, and then if I bring it up all the way, you'll see that we're now not going below the white line. It's an entirely positive wave, and the part of the wave that was previously negative just stays at 0. So we get a swell in volume, but outside those positive curves, we're just staying at a fixed volume of 50%. Alternatively, we could use the absolute value switch to invert the negative portion of the signal, which has the same effect of making the wave entirely positive, but instead of zeroing out the negative portions, we're inverting them, which has the effect, again, of doubling the rate of the LFO. And of course, if we change the base clock rate, we can get different patterns. And if we speed this up, especially with the absolute value switch on, we can start to get into sort of a tremolo territory. In the next couple of patches, we're going to look at ways to use warp 1 to improve a sequence by making timbral changes. We're using the granular formant oscillator on plates to create this melody, and I've got a bass line going in the background. And we're using both the main and the aux outputs from plates, which give two different waveforms. I'm sending them through the green and blue channels respectively so we can see them on data, and then we're sending them in to the two inputs on warp 1. We can use this to essentially mix the two waveforms together, and then we don't need a separate mixer module to create a more complex wave. We're then taking the output of warp 1, sending that through the yellow channel on data, so that yellow trace at the bottom is the output of warp 1, which right now is having no effect because we're not changing the exponent or the symmetry. So that's essentially just the green and the blue waveforms mixed together. We're then sending it through the quad VCA and applying an envelope from Quadrax just for the VCA. So this is just affecting the volume. I have the red mode engaged on the second channel of Quadrax, so it'll trigger at the same time as the first channel. And the output of that is going into the second channel of the quad VCA, which I'm just using for attenuation, and we're sending the final envelope into the exponent input on warp 1. So as I start to bring in the level, that second envelope will be increasing the value on the exponent, essentially giving us that overdriven soft clipping. Let's bring it all the way up for maximum effect. And so now the onset of the attack of each note will have a different shape from the processing of warp 1, and we can use the envelope controls to change exactly how that's applied. So we can have something that kind of comes in slowly, dies away quickly, and we can change how much of it we hear relative to the length of the entire note. Of course, we don't have to control the attenuation of that signal by hand. I've also got a triangle wave patched in here. And if we let that triangle wave modulate the amount of that envelope we're letting through, then we get a sequence where that onset comes in and out. So sometimes we hear that timbral change and sometimes we don't, based on how much of the signal is being let through the VCA. So far, we've been only using the positive part of the exponent control for that soft clipping, because we're giving it a positive envelope, but if we invert the envelope so that it's a negative voltage, then we'll go counterclockwise on the exponent and get that other sound. I'm going to use the sum diff to do that by unpatching the output from quadrax into the quad VCA, instead sending it through the CD channel and then doing 0 minus that voltage to invert it. So now we have a completely different timbral sound, which we can still control in the same way. You could also experiment with swapping the polarity of that envelope in time with the music to give you different types of wave shaping by controlling that exponent counterclockwise and clockwise. This patch is a variation of the last one, or using modulation into warp 1 to create timbral changes to increase the interest of a sequence. But in this one, instead of sending an envelope to change the timbre for right at the onset of each note, we're going to be taking 4 random stepped voltages from Pamela's Pro Workout coming out of these 4 channels, sending them into the quad VCA for attenuation, and then sending those into 4 different parameters on warp 1. The first channel goes into the exponent, the second channel goes into the second input, which effectively controls symmetry, and then the third and fourth channels are going into the negative and positive clip, respectively. Right now they're all the way down. We bring up the filter all the way so we get the full spectrum of sound. And then let's start modulating the exponent. This is just a random value per note. Now let's modulate symmetry as well. You can change the position of the potentiometers on warp 1 to set a different offset where the modulation will be based. And you can try playing with the scale for different effects too. Alright, let's try modulating the clip. So now the positive and negative portions of the wave will be randomly clipped at different points for each note. In this last patch, we're going to be using warp 1 with some self-patching to create a sort of pseudo-random source of voltage that we can feed into a sample and hold and a quantizer to drive a pitch sequence. I've got a baseline going with beads wavetable mode off screen, and then what we're seeing here is a triangle wave, bipolar, coming out of oct into our green trace on data with kind of an arbitrarily selected rate. We're sending that out into the main input of warp 1, and then sending the main out of warp 1 into the second trace on data, that's the blue waveform. And then we're taking the inverted output of warp 1 and sending that back into the second input so that the triangle wave and the inverted output are going to be mixed back in on the input to further influence both the output and the inverted output. That's essentially generating this pseudo-random looking wave. We're then sending the voltage created by that into the sample and hold on kinks, and I've got a clock off screen that's triggering the sample and hold. So every time the clock comes in, we're going to grab a voltage from that. We're sending the sampled voltage into the barred quartet's first channel, which is just programmed to a minor scale, and it's sending the quantized voltage out into plates as volt per octave. I've also got this trigger set up so that every time the pitch on barred quartet changes, it's going to send a trigger out on this cable into the plates trigger and we'll get a new note. And then finally, we're just sending the audio through Desmodus Versio for a little bit of atmosphere. I've got some drums going off screen. So in this case, the melody coming from plates is being driven entirely by this random waveform, or pseudo-random waveform, coming from data and being sampled and held. The knobs on data will then influence the range and the contour of the melody. So going counterclockwise on exponent, we start to go into a higher range, but because of the quantization, we'll still stay in scale. Turning clockwise will make notes a little less frequent and tend to stay a little more anchored around the bass line. Even though we're sending in the inverted output into the sort of symmetry input, we can still apply an additional DC offset to again influence the bass line and the range of the melody. So turning up the symmetry, you'll start to hear really high pitches sprinkled in, and similarly turning counterclockwise, we'll stay in a lower range. Scale, of course, will also affect the sound. This is kind of a similar effect as the exponent, getting pitches kind of randomly in the higher range. And clipping will have a similar effect. Clipping the lower portion of the wave means that those lower pitches will be chosen less often. And similarly, the positive clip will keep the high pitches from being triggered as often. It's important for this that we're in the hyper mode, which causes the really extreme amplitude changes of the wave. You can see if I switch into direct mode, we just end up with the triangle wave signal we started with. So this gives us a way of really performing by modulating the controls on Warp 1 to change the melody. I hope you enjoyed this deep dive into Warp 1, and I hope it gave you some ideas for how to use it in fun and interesting ways. If you found the video valuable, I hope you'll follow along for more like it. I'd also very much appreciate your support on Patreon. You can join for free, or chip in a few dollars a month for step-by-step patch notes for videos like this one, high-quality audio downloads of every musical performance posted to the channel, sample packs, full access to Discord, and more. Check the video description for details. If you want to get Warp 1 for yourself, you can also support my work by ordering one from Perfect Circuit using the link in the video description or the pinned comment. This will earn a small commission for me at no additional cost to you. Thanks so much for watching. See you next time.